Hello, my name is Iman. I'm going to present our paper evaluating machine learning based IoT device identification models for security application. This is a collaborative work, Imperial and Georgia Tech. Sorry, how does this work? Oh, okay. So imagine you are a network operator responsible for a warehouse, 1,000 IoT devices under your responsibility, and a new vulnerability discovered targeted specific type of IoT devices under your management. So as a network operator, how would you solve such a security vulnerability? First, you need to identify all IoT devices affected by such vulnerability. And then you run a security patch to fix it. So the question here is how accurately your IoT device identification solution would be able to retrieve all the IoT devices affected. So it is crucial for you as a network operator to identify all devices in such security threat. So let's have a look at the current IoT device identification. IoT devices identification solution can be static, rule-based, or machine learning. But wait a sec. Static, they face deployment challenges because you need to regenerate them before using them. And the machine learning one, they are experiencing challenges in adaptability and spatial-temporal validation, changing the environment, and different network conditions. So we observed that 70% of the current IoT devices identification are machine learning based. In our paper, we focus on the machine learning based devices. In particular, we ask ourselves whether the current IoT devices identification solution can be used by the network operators in real-world deployment. So let's have a look, what does it mean, real-world deployment and practical model in real-world? So we did a literature review, and we found that the practicality model is a model ability to ensure robust and reliable IoT device identification across different operational modes, deployment environment, and network conditions. So from this definition, we can extract specific attributes like robust, reliable, different modes, and deployment environment and network conditions. So we ask ourselves what defines a robust and reliable solution, and what do varying modes and deployment environment mean, and what network conditions must a solution consider. So we've been looking at the prior work and researchers, how they define such attributes, and we found people were looking at generalization, cost metrics, ethics and societal impact. But wait a sec. Does those all apply for IoT context and real-world deployment? What we found is the most common when it comes to IoT and real deployment are generalization, robustness, and stability over time. So basically, what does it mean in the context of IoT? So it means we need to deploy a solution that can be generalized across different environments / configuration simultaneously with robustness and performance and stability over time. So let's look at the different environment configuration when it comes to IoT devices. First of all, devices, they experience different mode of operation: user interaction, non-user interaction, setup mode, and reset. So the question is whether the current model can generalize across those different life cycle of the IoT devices. And we call this the mode of operation attributes. The second question would be, if we train the model on a specific network, would it be generalized at different network, ISP, routers, geographical locations? And also, if we train the model now, would it be robust for a year later, 2 years? And we call this transferability. The last, network usually experience different conditions. For example, like packet loss, packet delay, or as a network operator, I might sample my traffic. So if I train my model in an ideal scenario, no packet loss, no packet delay, and no sampling, would it be robust in sampling, packet delay, and packet loss? and we call this observability. So in our paper, we define a practical model as a model can be reliable and robust across those three attributes: the mode of operation, transferability, and observability. So we have a definition of model, like a practical model. So let's have a look how we can evaluate the current IoT devices. So looking at the current ML-based solution, there are three main components. First, dataset. What dataset should be collected and how we should be collect this dataset. And for this, we created a dataset from both labs in the UK and the US. We ensured same identical devices, aligned the mode of operation of both devices, and also synchronized the time collection, and we have the same testbed configurations, because we want to enable rigorous evaluation and feature analysis. The second component is the model. So the question would be what model to be used and how complex should it be. And for this, we reviewed 200 papers, and then we filtered them to only IoT identification device solutions paper, and then we further filtered them on the seminal work, the first to use the model, the first to use the features, or the combination of them. And then we looked at the code of these papers, and we found 2 public running fine, and then 1 we had to do a few modification, and 7 we had to re-implement from the scratch using the original paper description, and there were 4 no sufficient information about the feature extraction. So we ended up evaluating 10 papers for the current IoT identification solution. The last component are the features. So what we mean is what feature to extract, the feature representation. For this, what we did is we used the exact method mentioned in the paper because we want to ensure they are identical for rigorous evaluation and also for the feature analysis. So for each of these papers, we have a baseline reproduced as close as possible to the original result of the paper. And then we performed several experimental evaluations across the 3 attributes. So for the mode of operation, we started to train the model for both samples, idle and active, and then we tested against idle alone, active alone, and mix. For transferability, we have spatial transferability, where we trained the model in the UK and tested against the US, and vice versa. And for the temporal transferability, we trained the model and we tested against different time period spanning from 1 week up until 52 weeks. For the observability, what we did, we trained the model on full sampling, and we tested against 100, 1,000, and 5,000 sampling. So we ended up in a total of 140 experimental against those 3 practical attributes. So let me now give you a brief of the key finding of the evaluation. You can refer for the data for our paper for the full details. For the mode of operation, we observed that the idle and active modes, they introduce behavioral shifts that reduce the performance. And for the transferability, we observed that the spatial degradation can be between 7.5% up to 74%, and for the temporal degradation begins after 1 week and worsen after a year up to 86%. And for observability, when we use sampled traffic, it reduced the performance by an average of 70.90. We anticipate such a degradation, but not to this much. So let me now just delve into one of the key findings, the mode of operation. And imagine again you are a network operator and you use one of the paper under evaluation. So let's say the MED paper, where they are using a model, using light GBM, and features incoming packet, incoming bytes, the TCP flags, and the port, and the IP address. And then you trained your model using a sample from active and idle from both lab and fault sampling. And you tested your model against the idle alone, active alone, and the mix. And you observed the following results, that your model randomly classifying when it's idle and active, and fairly good when it's mixed. So what we did to understand what happened, we looked at the data, and what we found is devices tend to remain in idle mode for longer periods than the active mode. Also, in active mode, devices tend to experience many different distributions. So our recommendation for the network operators and for us as a researcher when thinking about the problem is to train the model in idle mode at different time and do the prediction, because devices tend to stay longer in the idle. So we can see there is a performance degradation, but what is important is like how to improve. So let's go back to the components of the ML base. The dataset has its own challenges, privacy, real-world collections. And for model, we observe that as a researchers, we tend to put more effort in the complexity of the model. So what we did is we focus on the features and we use explainable AI and the features' importance to pinpoint this performance degradation and also to see how we can improve. So let's go back to the mid-paper, and we started by plotting the TSNE. And as you can see, there is no separation between the device type. These are clusters, neither grouped, neither distinctly separated. So what we did further is we plot the SHAP for the features, and we observed that 33% of the features have zero SHAP, which means they don't do anything in the predictions. We do more feature permutation, and you can look at our paper, and we observed the same behavior in both the training dataset and the testing dataset. So the key findings overall was that researchers tend to use simple features such as mean and variance, and those basically they fail to capture the nuances in the distributions. So we recommend to avoid those first-order features, mean and variance, but instead use features like entropy and kurtosis because they can capture the nuances of the data. Our paper have more insightful and recommendation. I encourage you to look at the paper and read it. And by this, I shall conclude my presentation and thanking you for coming and listening, and I'm happy to take your questions.
Question. Thanks for your presentation. My question is that this is about device identification. I'm wondering, identification means you can specifically distinguish one specific device from the other, or you only can classify the device types?
So basically, device type can be various. So either you differentiate the model of the device, so you can say this is Amazon Echo Show, or you can just say this is a smart speaker based on the functionality.
Yeah, so my question is that, for example, for the smart speaker, you have 3 smart speakers. They are from the same vendor. Can you identify each specifically?
You mean like my work or like the work that we evaluated? Because we adopted, we've been evaluating what people have been doing, and it's been basically some of them, they've been looking at the problem from functionality perspective, some of them they've been looking at the type perspective, so it depends.
Okay, yeah, thank you. So a following question is about, you're talking about the transferability. So is there any mitigations or suggestions how to improve the transferability over a long period?
Which transferability are you talking about? Is it spatial transferability or temporal? Because it's different.
I think now you test 1 week, right? For the testing suite, you test 1 week. So how about 1 month or half a year?
Okay, so for transferability, you're talking here about temporal one. And basically, overall, you need to retrain your model and update your data ASAP, within maximum 1 to 2 weeks. Other thing you can do is the model to use. If you're looking for long-term, you can use a model like the light GBM because they tend to capture the longer period. And if you want more robustness in a shorter period, you can use random forest because they're really good when it comes to shorter time period as they don't tend to overfit. Does that help?
Thank you. Yeah, it helps.
All right. Any other questions? Yes.
I was wondering for the spatial transferability, you showed that it degrades a lot. but you did your best to keep everything same in those two test cases. So do you have an insight what caused the degradation?
Yes. So basically what we notice is when we talk about like specific features in the US and in the UK, they're sometimes overlapping, confuse the model. So they can't tell whether this is the UK or the US. And in other cases, what we observe is no, they can capture the nuances. For example, like we found some destination ports specifically been used in the US, not been used in the UK. So that was at some point helpful. And the other way around, there are some features, like I said, again, confusing the model, so they couldn't tell whether this is Amazon Echo in the US, but it might be like TB-Link in the UK. And also, what we found is the number, for example, like of domains contacted in the US is a lot compared to the UK. So when you train your model in the US and move to the UK, it's more likely to see these domains in the UK, but not the other way around.
Okay, thank you.
All right, thank you so much. Just one more round of applause. And